I'd like to thank Neda, Masood for this kind of invitation. These seminars have been very lively, and I enjoyed the ones that I've been able to attend. And so I hope that this continues. This has been a very nice exercise, and I think it helps to share our interests, results all over the world. So hopefully, Neda, Masood, you can continue with this effort for the near future until we can see each other in person.
Okay.
So
thank you very much.
Thank you. The idea then is to talk about this topic, which has become of worldwide interest, so to speak, that has to do with the spin properties of hadrons that can be detected in heavy ion collisions. Because, as you all know, in peripheral collisions, you can produce a large vorticity. And the question is whether this vorticity can be detected by means of the spin properties of hadrons, in particular baryons or hyperons in this case, but it could also be, of course, vector mesons. So the motivation is then the recently measured properties of lambda and anti-lambda polarization in peripheral heavy ion collisions performed by the beam energy scan program of STAR at REC. And so motivated by these results, which were, to my opinion, very interesting and surprising, we started thinking about ways to understand these properties. So this motivated 3 works, which I list here, and with different sets of colleagues. And as we go along, I'll try to make to emphasize what are the what are the steps that we were taking in order to understand this data. So let me just briefly mention what is this original motivation, and the motivation made the cover of Nature because what the STAR collaboration measured back in 2017 were the global lambda polarizations, and the interest came by because from their measurements, it became clear that these collisions produce not only extreme situations for other quantities, such as, for instance, temperature or perhaps magnetic fields, but also large vortical motion. And so the angular velocity, which was inferred from these results, is the largest one ever measured for a system, for a physical system. Let me just try to put it into context. What does it mean to have an angular velocity of order of 10 to the 21st seconds inverse seconds? Well, you see, for other kind of experiments, lab experiments, like for instance, superfluid nano droplets, the largest angular velocity that can be produced is of order 10 to the 7th inverse seconds. Then this number becomes smaller for other systems, like for instance, turbulent flow in superfluid helium-2, which is of the order of 100 inverse seconds, and so on and so forth. For instance, of course, this is another kind of systems, but the great red spot in Jupiter, it's only 10 to the -4th inverse seconds, and so on and so forth. So you can see that there are many orders of magnitude of this angular velocity, which was inferred from these heavy ion collisions compared to other systems. So what is the origin of this vortical motion? Well, if you have a peripheral heavy ion collision, what you have is an imbalance in matter, say the projectile nucleus and the target nucleus move in opposite directions. So when the matter in a given peripheral collision, when you have a strip of larger abundance of nuclei in one of the colliding of nucleons in one of the colliding nuclei, what you have is some linear momentum which is imbalanced, so to speak. So it goes in one given direction, but if you go to the opposite side in the impact parameter direction, you have the reverse situation, and then the fluid starts moving, or at least it has some angular momentum, initial angular momentum. It will depend eventually on the properties of the fluid, whether or not this rotation keeps going on. But at least from the beginning, you can see that you have a large angular momentum. And the question is then whether there is spin-orbit coupling to try to translate this angular motion into spin degrees of freedom. And how this can be achieved, this is the subject of the talk. But before I go into those details, I want to point out that in order to measure such transferring of degrees of freedom from angular motion, angular momentum motion to spin, you need some probes, and one of the most interesting ones is the lambda particle, of course, and its anti-particle. Because this is like self-analyzing system, so to speak, in such a way that it is produced by strong interactions, but it decays weakly. So the decay, most of the times, the decay involves two charged particles, protons and pions, or antiprotons and positive pions. And so if you measure them, of course, this will be after after a given number of centimeters, which is also nice because then it'll allow you to do some reconstruction, which is rather, well, more simple than other kind of systems. Then you can measure the charged particles in your tracker. And because the decay is weak, it violates parity. And so the angular distribution has a dependence on the angle between the decay products. And if you measure such angular distribution, then you can measure both, well, knowing that the decay violates parity, you have a parameter there, which is well known. And then by measuring this angular distribution, you can measure the polarization. This is rather nice, and it's been used for a long time already to try to understand what are the spin properties, well, what is the role of spin when you produce hadrons in other kind of systems, from E plus E minus collisions to proton-proton collisions, and in this case, in heavy ion collisions. So as I said, these kind of properties make this system ideal to study the transferring of spin, of angular momentum to spin properties. Moreover, I want to point out that the quark content of the lambda is also nice in the sense that it's the lightest of the hyperons, and so lambda is made out of an U, a D, and an S quarks. So it's the first, well, the lightest particle which has these three different spin, quark content. And because of that, it is believed that the spin properties of the lambda are carried by the S quark in such a way that the properties of the S quark combine with the di quark formed by the U and the D. And so all of the spin of the lambda is carried by the S quark. So this is nice because then if we can try to see what happens to the spin of the S quark, then we can perhaps relate directly these spin properties to the spin properties of the lambda. And this is the data. And so let me just walk you through. It's rather interesting to mention what are the properties. You see, in the left plot, what you see is the average polarization. This is the so-called global polarization. Now, the global polarization, as you can imagine, the polarization is can be oriented. It's a vector, pseudo vector. It can be oriented in any direction. So you can choose the direction and then project the spin direction of your particle, the particle that you want to study, onto that direction. And when you do that, then, well, you have a freedom to choose the direction. For these purposes, what the star collaboration chooses is the direction which points out normal to the reaction plane. This is the so-called global direction, global polarization, because, well, this is more or less in the direction of the angular momentum that that the collision produced. So taking that as the direction of the polarization, you see rather interesting features of this polarization. For large energies, and of course, these are semi-central collisions. You see, this is gold on gold, 20 to 50% of the total cross-section, which is corresponds to an impact parameter of order, say, 10 Fermis. So you see that for large energies, the polarization is consistent with zero. So there is no net global polarization, neither for lambda. Energy decreases, and this is the beauty of the beam energy scan program. You start seeing something which is consistently non-zero, both for the lambda and anti-lambda polarizations. Then if the energy decreases even further, you start seeing a deviation which is, at least for energies between 10 and 100 GeVs per nucleon, which is, say, within error bars, the polarization of lambda and anti-lambdas are basically the same, but then you go to energies below 10 GeVs, and then all of a sudden, far from being consistent within error bars, you see that the anti-lambda here in this red spot the polarization is much larger than the polarization of the anti-lambda. It's a factor of 4, more or less. And let me just remind you that this is the percentage of polarization. So in other words, it's a small polarization, but you can see that there is a huge deviation from the polarization of the anti-lambda as compared to the lambda. And on the right-hand side, what you can see here is that this is a phenomenon which is associated to the centrality of the reaction. So for a given collision energy, say the largest one in REC, 200 GeVs, you see that the global polarization for central collisions of lambda and anti-lambda are basically the same, but they start deviating. They are consistent to be equal to each other, say. Let me remind you, we are talking about the largest energy. But as you can see, when the centrality increases, and these are peripheral collisions, then the polarization, both for lambda and anti-lambda, start being different from zero. So this overall tells us that this phenomenon has to do with the impact parameter of the collision, and therefore the idea that it is related to this vertical motion that I talked about at the beginning. All right, so let's see, let me just show you that this, of course, is a subject that has attracted a lot of attention, because the idea is to try to see what happens. Why is it that these polarizations are so different from each other when you decrease the energy of the collision? And so here I just want to quickly show that the interest is large. Different groups have been trying to pursue a reasonable explanation with different degrees of success. But I think that it's fair to say that most of these calculations do not really show what is happening for the lowest energies that we have data from. So this is a challenge still, and it's fair to say that it's not well understood, or at least that the mechanism behind this behavior is not well understood, and this is what we want to try to address. All right, so let me just jump into the details of the calculation that we pursued. And this slide is to summarize the results and the ingredients, because I'll try to walk you through the different elements, but I don't want to lose you in the woods. So I encourage you to stop me whenever something is not getting across. And but in order to achieve that, I'd like to tell you in a nutshell what are the ingredients and what are the results. So the ingredients start from a modeling, and what we will be talking about, or what I will be talking about, is that in a peripheral heavy ion collision, what you can think of in simple terms is that the collision region, here represented by this ellipsoid, which shows different colors, green, yellow, and orange. This interaction zone is composed of different density, particle density regions. There is a less dense region, which is called the corona, right here. And as we move into the most central part of the collision region, then the density of participants starts increasing. And then we reach the highest density in the so-called core. Of course, the distinction between corona and core is a density-associated phenomenon. So there should be a critical density when one can speak about passing from the corona to the core. And it's also this critical density is also associated to the formation of quark-gluon plasma. So we will be introducing such critical density based on earlier results that have been making use of these kind of ideas, and then in such a way to distinguish between core and corona. Now, why is this interesting? Well, you see that if we plot the number of particles, in this case lambdas, coming from the corona and the core, we see that for a given energy, and this is of course true for most of the energy that we can study, but say for a small energy, a small collision energy, the blue line here, which represents the lambdas produced in the corona. Here I'll speak about why we chose this way of labeling these processes. It says it's difficult to read, but it says REC, recombination processes. So lambdas will be coming from what we call recombination processes, and I'll speak about that in a little while. But for the time being, just think of them as coming from the corona. So the blue line represents the number of lambdas coming from the corona, and you see that as the impact parameter increases, the number of lambdas coming from the corona becomes larger than the number of lambdas coming from the core, which are associated to QGP processes. So the number of particles, in this case lambdas, coming from the QGP fastly decreases as the impact parameter increases. And so at some point, the processes coming from the corona meet, the number of particles coming from the corona meets the number of particles coming from the core. So at this point, which is the impact parameter of interest for these peripheral collisions, you can see that when the core meets, when the core meets the corona, the abundance of lambdas reverses. And this will be a very interesting feature, because then if you take into account that, in other words, that there are two regions that produce particles, then this has impact on the polarization properties, because if the polarization properties from the core or if the core gives different polarization properties to the lambdas than the corona, then of course, when you change the abundances, something is bound to happen. Then, of course, this is not the end of the story, because in order to put these ideas into the description of the polarization, what you need to do is to keep track of what is the polarization of the S quarks that are produced either in the core or in the corona. And so for that, you need to do a calculation, a field theoretically motivated calculation at finite temperature and density. This is important because at low energies, we know that the baryon density is important. So for that, you need to give an estimate of what is the relaxation time. In other words, what is the time that S quarks take to align their spin to the global polarization? And for that, you need to do the calculation of, well, in this case, an interaction rate, and its inverse should be associated to the relaxation time. So if the relaxation time is small enough compared to the lifetime of the system, then there is a good chance to make this alignment possible. And so for that, I'll introduce a field theoretical calculation at finite temperature and density to estimate such relaxation time. Well, there are two other ingredients that I'll speak about later. That has to do with how we estimate the abundances of particles coming from the core and the corona, that is lambdas coming from the core and the corona, and also anti-lambdas, of course. But when all of this is put together, the final result that I want to show you is summarized in this lower plot. What we find is that if we consider that the lifetime of the system, here represented by this T, is between 1.5 and 4.5 Fermis, then putting everything together and the relaxation times that I talked about, and all of the ingredients that I'll speak about, then we can have a reasonable description of the so-called excitation function of the polarizations, which is in good agreement with the experimental data. So let me go and try to give some details, but I saw that there were some raised hands. So if you want to...
Yeah, there's a question by Farid Tarinavas. So
yes,
Farid.
Sorry. I have a question about the density of particles coming from the core and corona. It seems you call it the particles density would be created the corona part.
I'm losing you. It's perhaps because of the internet connection. But can you repeat your question again?
I want to know.
So Farid, your connection is not very good. Maybe you can write your question in the chat box. The connection is not so good. We can't hear you.
I think that question different. Do you hear?
Farid,
okay.
Farid, we cannot hear you. Farid, we cannot hear you because of the connection.
I can come back to your question anytime you want. It's perhaps a better idea if you write it up, and then perhaps Neda or Masoud can read it to me, and then I can answer it. That's no problem. I can come back anytime. So just write it up. All right. So let me move on. So those were the basic ingredients. There is a couple of more ingredients that I'll talk about, but let me just walk you through them in greater detail. So the main idea is that we have a two-component source. Lambdas or anti-lambdas can come from the core, and what we will assume is that if they do, then these will be mainly processes driven by QGP. And in other words, when you have a QGP, what you have is, say, in simple matters, you have freely roaming quarks. And so the way they form baryons is through processes which are not available for collisions of simple systems such as PP. So if you have a fluid which contains freely roaming, between quotation marks, freely roaming quarks, then they can recombine. They can combine, sorry. They can glue together, and then they can form particles. Now, this we will call QGP processes. However, in the corona, where the density of particles, of participating particles is not that large, then the processes that produce lambdas and anti-lambdas are closer related to nucleon-nucleon interactions. So these are PP processes or PN processes and so on, which have a different yield, a different abundance of particles. See, in PP processes, it is believed that lambdas are formed by so-called recombination processes. So you have a PP collision, and then what can happen with a larger probability is that a U and a D quark, which were already present, they were valence quarks in the reaction, pick up from the C an S quark. So it's easier to pick up an S to form a lambda than to pick up 3 anti-quarks, an anti-U, an anti-D, an anti-S, to form an anti-lambda. So the abundance of lambdas created in the corona is gotta be larger than the abundance of anti-lambdas. And that will have an impact in the polarization properties, as I'll try to show. So is there any question so far? Perhaps Farid has some question, or he was able to post it in the chat?
No, that's, I think.
Right. Okay, so I'll continue. All right, so this is...
So the question, sorry, Alexandra.
Yes,
so
yes.
The question came. So my question was about the criteria of core and corona, or what he referred by densities, he wrote.
Right.
And
right. Yes.
Since it seems naturally that always core must have greater outgoing particle than corona.
Right, excellent. So yes, this is a very good question. And as I tried to mention, but I of course didn't stop in the details, the criterion has to do with the particle density. So there's got to be a critical density from starting from this density. In other words, for larger densities, then you can speak about QGP. You see, the QGP is a density, particle density, not baryon density. Particle density driven phenomenon. So if you have a very dense system, and of course you can achieve that dense system when you have a larger number of participants, then you can have the melting of the participating nucleons, and therefore speak about the possibility to form a QGP. But if you are below that critical number of participants, then the system is dilute. And because of that, then the processes that take part will be more like processes in proton-proton collisions. Now, this said, one has to remember that this, in this model that I'm referring to, core and corona, there is a full correlation between the number of participants, in other words, something that goes above this critical number of participants and something that is below, with the geometry of the collision. But in a more sophisticated implementation of these kind of ideas, this is this doesn't need to be this way. In other words, we know that at least for large energies, one can have the possibility of fluctuating density regions. So event by event, you can have different fluctuation, different collision, density zones in a collision. And therefore there is a perfect correlation between the geometry of the collision and these density hotspots. But it doesn't matter in such a way that the beauty of this model is that there is a perfect correlation between geometry and this hotspot. But the results shouldn't depend on that, because if you don't have such perfect correlation, you can still speak about these hotspots and then follow or try to keep track of the particles that are produced from different density zones. And so the idea should be pretty much the same. I know that I went a little bit ahead of myself, but I'll try to come back if needed along the talk. All right, so let me retake. And what I'm trying to explain to you is that the number of lambdas can be broken up into two different components. One that comes from the QGP, which we call the core particles, and then which come from the corona, and these we label as recombination kind of processes, so which are more related to PP collisions, so to speak. All right, and so the polarization, of course, given a direction, and in this case it's a global direction, the direction of angular momentum, the perpendicular to the reaction plane, is the difference between the number of particles with spin pointing along that direction and the number of particles with spin pointing in the opposite direction divided to the total number. And so each one of them, n upper arrow and lower arrow, have two different sources, and these are these two sources that I just referred to. And therefore we can write the polarization of lambdas and anti-lambdas, accounting for those different origins of the particles, which are here written explicitly. So this is the total number of particles pointing with their spins in the direction of the normal to the reaction plane. It has the two components, and these are the number of lambdas with their spins pointing opposite to the reaction plane, and it also has the two components, and the same for the anti-lambdas. Now we can do a little bit of algebra. This is easy, because then we can separate the polarization coming from recombination kind of processes, in other words, the corona. And if we do that, then we just shuffle the terms that appear here, and we come up with this extra term here in the numerator. And in the denominator, we have this ratio, the number of lambdas coming from the core to the number of lambdas coming from the corona, and the same for the anti-lambdas, right? So what we did was just to define the natural definition of the polarization of particles coming from the recombination processes is this one, and the same for the anti-lambdas. All right, so this was just algebra, but let's explore the consequences. See, when particles come from the corona, they come from processes which are mainly nucleon-nucleon processes. And we know that for many situations, for instance, HICs production or whatnot, these kind of reactions are less efficient to bring the system into equilibrium. So in other words, even though we have a large portion of nuclear matter that is partaking of the collision in the less dense zone, and that these particles also take part of the vertical motion, the processes to align their spins, even though they are swirling around, as a consequence of the angular velocity of the medium, the cold nuclear medium, are less efficient. So what we will do is to assume as a working approximation that the polarization coming from recombination processes, both for lambdas and anti-lambdas, is equal to 0. This is a working assumption, but I think it's well motivated from these other results that I referred to. So you see, in the numerators, we get rid of this term and this term. And we just come up with this simpler formula. All right, so now we have to compare in the numerator, we need to do something about this difference, both for the lambdas and the anti-lambdas. Let's proceed. So you see, this is something that resembles the polarization of the lambdas from the QGP. So we can convert that if we introduce something here in the denominator that has to do with the total number of particles coming from the QGP. So let me do that. Let me introduce the concept of the intrinsic polarization for the lambdas, which is the Z. We name it Z. And this is introduced by taking this difference being divided by the total number of lambdas. And also we do the same for the anti-lambdas. All right. So these numbers, as I will show, are going to be small, but finite. They are not 0. And what I'll do in the second part of the talk is to compute them from this model in a finite temperature and density. All right. Now, let me make an assumption. This is not a perfect assumption, but this is nevertheless some working assumption in order to avoid introducing extra parameters. Let me think that the number of anti-lambdas coming from the QGP is more or less the same as the number of lambdas coming from the QGP. In other words, because these are processes in which you have freely roaming quarks or anti-quarks, it'll be as easier to form anti-lambdas than lambdas in the QGP. Now, I know that in equilibrium, and especially at finite baryon density, there will be corrections coming from the chemical potential. That is true. And it's something that can be also introduced in the model. But in order to avoid introducing extra things, let me just work with this assumption, and then eventually, if our results are, say, reasonable enough, we can refine the assumptions. But for the time being, let's do that. Then what happens? What happens is then that what we can do is to plug in that assumption into the previous equation right here. And again, just from algebra, put in here a Z factor and here a Z bar factor to the expense of introducing the number of lambdas coming from recombination. You see that that was here already. That was here already, right? And so these formulae for the polarization of lambda and anti-lambda become a little bit more transparent. All right.
Sorry, Alexandra.
Yes, please.
Sorry, there's another question. Farid again asked, why is there any fundamental reason for the difference of the number of lambda and anti-lambda? Why do you expect that the number are different actually, and you make this
in the QGP?
Yes.
Yes, it's a very good question, and yes, there is a fundamental reason. You see, when you have particles in equilibrium, in other words, in thermal equilibrium, the number of particles is related to the number of antiparticles because of the occupation numbers. These are fermions. So you see, for a given energy, imagine that the particle is at rest. So it doesn't have any momentum, and therefore the energy is just the rest mass. And the occupation number for a particle, a fermion, is related to the chemical potential. And the relation is that you have the Fermi-Dirac distribution. You have 1 divided by e to the energy, that is the mass, minus the chemical potential. This exponent is divided by the temperature, and then you add a +1. That's a Fermi-Dirac distribution. But for the antiparticles, you have the opposite sign in the chemical potential. So what you have for the occupation number is 1 divided by e to the mass plus the chemical potential divided by temperature, and everything +1 in the denominator. So you see, the occupation numbers are determined by the values of the temperature and the chemical potential. And we know this is the baryon chemical potential. And we know that the baryon chemical potential is large for collisions of small energy. So the ratio of particles to antiparticles is determined by these occupation numbers. There are deviations from this assumption in which I am taking this number of antiparticles and particles to be equal or very similar, which are introduced by these values of the chemical potential and temperature. But you have to keep in mind that the mass of the lambda and anti-lambda is large compared to the chemical potential. So to first approximation, if you sum or subtract the chemical potential to the mass of the particle, you're just subtracting say a fraction which is about a third or perhaps a little less than the mass of the particle. So for our purposes, this assumption will suffice. But of course, if you want to refine it, you have to take into account thermal equilibrium. Was I clear enough?
I think so. Yeah.
Okay.
Sure. Yeah.
But nevertheless, you can
yes.
stop me anytime you want.
Sure. Thank you.
All right. So with that assumption, then what we need now is to recall that the particles coming from the corona are not experiencing the same kind of conditions that I just referred to. In other words, the number of anti-lambdas coming from recombination processes are related to the number of particles of lambdas coming from recombination processes by some factor. And in this case, we cannot assume that this factor is something. We have to resort to experimental data. And because these processes are very similar to nucleon-nucleon processes, then we can resort to PP collisions to try to see what is this W factor as a function of energy. So by doing that, you see that now the polarization of lambdas and anti-lambdas start looking similar, but with differences. And the main differences that I can point out here are the following. One is the intrinsic polarization of lambdas, which is coming from our assumptions from the intrinsic polarization in the QGP of S quarks. And the same for the intrinsic polarization of anti-S quarks from the QGP for the anti-lambdas. But the factors that are a little different from one polarization to the other have to do with this W factor, which accounts for the proportionality between the anti-lambdas from PP collisions or from corona processes and the number of lambdas from corona processes. So although they look the same or similarly, you have different Z and Z bar factors. You need to compute them. And then you need to estimate what is this W factor. Of course, W is expected to be smaller than 1 from what I mentioned. In other words, it's more difficult to pick up 3 anti-quarks from the C than just a S quark from the C to produce an anti-lambda compared to a lambda. And so this W factor should be smaller than 1. And we need to resort to some experimental data, and we do. So this is a combination. These are all of the references from where we took this data. These are PP collisions. And you can see that the ratio of anti-lambdas to lambdas as a function of energy from the energies of interest for the beam energy scan program to large energies follow this trend, and this is a parametrization of a fit to this experimental data, which looks this way. Here it's a logarithmic fit, These are the parameters of the fit. And as you can see, indeed, the number of anti-lambdas compared to the number of lambdas is smaller than 1 for all of the collision energies of interest to the data we want to describe. So this is nice. We were able to compile this experimental information and to verify that indeed omega seems to be smaller than 1, and this is going to be interesting. All right. So why is this interesting? And this is the proof of the principle, so to speak. Imagine that we put together all of these ingredients. In other words, we know that omega is smaller than 1, therefore its inverse is larger than 1, and therefore we can try to test whether with this information we can produce an anti-lambda polarization larger than the lambda polarization. So there's got to be an amplifying factor, so to speak, and this is true. See, if you remember the equations that I came with, it involves a 1 over omega. If omega is smaller than 1, then it seems to be an amplifying factor for the anti-lambda polarization. But we need to, of course, try to see what is the correction to that amplifying factor from this 1 over omega W factor that is down here. And so we proceed to do that. So let's imagine that Z and Z bar are equal to each other and that they are smaller than 1, so 0.1. And this is a red curve. And plot what is the ratio of the anti-lambda to the lambda polarization as a function of omega. And you see this remarkable property. You see that if omega was 0, then you have the largest polarization, but for all of the region of interest of omega, the ratio of polarization is larger than 1. So this is very nice. There is a window of opportunity where these omega properties, this 1 over omega amplifying factor, produces that the anti-lambda is larger than the lambda polarization. This is very nice. But okay, so this is not a proof of nothing. Let's explore other possible values of the polarization. So as I'll show you, the anti-lambda intrinsic polarization is smaller than the lambda intrinsic polarization. This is because the anti-quarks, the anti-S's, align less fast than the S quarks with the angular momentum. And because of that, the intrinsic polarization turns out to be, for the S quarks, larger than the anti-S. So let's explore this case and imagine that the number of lambdas coming from the QGP is half of the lambdas coming from the corona. If you do that, and with these other two assumptions, you have the blue line, and you see it is still remarkable that there is a window of omegas, still smaller than 1, for which this ratio, the anti-lambda polarization to the lambda polarization, is still larger than 1. So there is confidence, confidence is building up, that these ideas may have some bearings on the results. So finally, imagine that the number of lambdas coming from the QGP is larger, 1.5 times larger than the lambdas coming from the corona, still with the same assumption that the intrinsic anti-lambda polarization is smaller than the intrinsic lambda polarization. And see, although the window reduces, there's still a window for which this ratio is larger than 1. So it seems that things are coming nicely together. And so we need to continue pushing for that idea. And so I'll proceed to do that. So far, are there any questions?
No, I think.
All right.
We can continue, yes.
Excellent.
We can continue.
You see, when I teach and I ask my students about this, I always start sweating because if there are no questions, then it may be that I already lost them. So please don't make me feel that. Don't make me feel like I'm sweating. If there are questions, please do shoot them. Don't keep them. These are simple ideas in the sense that they all rely on particle abundances. And what I've shown is that it seems that there is a window of parameter values for which this ratio can become larger than 1. All right, yeah, but are there any questions? All right, so I'll keep going, and please interrupt me anytime you want.
Thank you.
All right, so this is where the critical density that I believe Farid asked about. So if I want to know what is the number of particles that come from QGP processes and from corona processes, I need to introduce a critical density of participants. So when we have that the density of participants, of course, this is a function of the impact parameter and the vector that, this is a geometry thing, this is a vector which represents the interaction region. We are integrating over such vector. When this density of participants is larger than the critical density, then the particles that we produce come from QGP. That's what we're saying. So we need to integrate the number of participants as a function of this vector and the impact parameter. It's a two-dimensional thing. And this, of course, has to do with the overlap function. These are the density of particles in one and the other nuclei that are colliding as a function of an impact parameter. And so what we need to do is to introduce what is the cross-section for nucleon-nucleon collisions, and therefore the number of lambdas produced in the corona. This has to be written the other way around. This n lambda rec is proportional to this thing that we have here, times, of course, the theta function, the step function, that tells me that we are below the critical density. All right. So, but this is simple. This is just how to put the core corona modeling into some numbers. All we need is this cross-section, and there's information for this cross-section. All right. So let's come back to this polarization formulae. And so we know how omega behaves as a function of energy. And so here is an example of what you get when you introduce this critical density. There is a number associated to this critical density. I have it somewhere here, or not here though in the publications. But once you put in that information, and this is motivated by when you produce QGP in other kind of collisions and measured from other observables, such as, for instance, Jape size suppression and so on, then you can calculate what is the number of lambdas coming from the two different collision regions. All right, so we have everything except the Z and Z bar. And so what I'll do is to proceed to compute it. So let me just make a quick summary. From assuming that there are particles, lambdas, anti-lambdas, coming from two different density zones, then putting this information into the polarization formulae and assuming certain working assumptions which are reasonable and resorting to experimental data, we have been able to show that there is an amplification factor for the anti-lambda polarization. Everything, if we want to put everything together and compare it to data, then we already know the W energy dependence. We need to know what is the intrinsic polarization for particles producing the QGP. These are the Z and the Z bar. These are 4 particles. This is quarks, S quarks, and these are anti-S quarks. So we need to do that because this is QGP information. We need to do that at finite temperature and density. And so I'll move on to compute that. All right, so in order to do that, let us remember that the object of interest is the so-called thermal vorticity. which is hereby defined. This involves, it's like a rotational curl of the fluid velocity, but in order to have the proper Lorentz transformation properties, this fluid velocity has to be divided by the temperature. That's why it's called the thermal vorticity, and the quantity that represents the thermal fluid velocity is this beta. This makes up this thermal vorticity through these derivative operators. And if you imagine that the motion has constant W, it's like if it was a solid rotating with a constant angular velocity. And at a constant temperature, it's easy to show that the thermal vorticity is coupled to the spin in a given direction. It's just proportional to the ratio of the angular velocity to the temperature. And this is what we will be working with. Because we want to couple thermal vorticity to spin, we will use that information, modeling the motion of the fluid as if it was a rigid body with a constant angular velocity and a constant temperature. And so we want to put this into a field theoretical calculation at finite temperature and density. And for that, what it'll do is, I'll assume I have a quark, S or anti-S, here, but then this quark is in the thermal medium, and the thermal medium is such that it interacts with thermal gluons, and these are thermal gluons right here. When I say that they are thermal gluons, is that they are, their dispersion properties are modified by thermal properties, both temperature and finite baryon density. And these quarks interact with the gluons through some effective coupling. And the effective coupling couples the thermal vorticity to the spin. And of course, there is the usual QCD interaction, this gamma mu, the color matrices, and the strong coupling to put in this vertex right here. So once the problem is set up this way, then it's just straightforward. It's just cranking the wheel. Nothing special about that. The interaction rate for these quarks as a function of their energy is just given by this formula. It's the trace of gamma 0 times the imaginary part of this diagram, weighted by the Fermi-Dirac distribution as a function of the energy of the external particle. And a further comment is that because what we want to do is to compute the relaxation time, that'll be the inverse of this interaction rate once we integrate over all of the possible energies of this quark. But the final comment is that what I want is to think that this quark is free. In other words, here I don't dress the quark because I want to compute what is the time that a free quark takes to align its spin to the angular vorticity, thermal vorticity, through this interaction. So I don't want to thermalize the quark beforehand. It has to be a free quark right here. So the ingredients are the interaction right here and the fact that the gluons are thermal. And so this is well known for most of you. If it's not, please stop me. The thermal gluons are known to be different from vacuum gluons in the sense that they develop a longitudinal polarization, here represented by this PL. It's a tensor which is longitudinal in 3 dimensions. It's transverse in 4 dimensions, of course, as should be for a polarization tension of a gluon. And of course, the transverse part, which is reminiscent of the fact that gluons are coming, say, from vacuum. But these functions right here represents the strength of each one of these polarization tensors. And at finite temperature and density, they are given by these equations right here in the HTL approximation. So I'm working in an approximation that where the mass of the quark is small, in fact, vanishingly small, compared to the temperature and the variance density. And so these are the well-known expressions for the HTL approximation of these functions right here. What I have to emphasize is that the capital K squared is the momentum for vector at finite temperature. So we are working in Euclidean space. And M is the thermal mass of the gluons. Omega n, of course, are the frequencies, the Matsubara frequencies associated to the gluons. All right. So more specifically, these functions Q0 that appear everywhere here are well known. They are in the textbooks. And these are the Legendre functions of some kind. And this is the expression. And M is the gluon thermal mass. And this is explicitly its expression as a function of temperature and baryon density, quark density. And these factors CA and CF are the Casimirs for the adjoint and the fundamental representation. G is the coupling constant, strong coupling constant. Here, we are taking G squared divided by 4 pi equal to the alpha strong equal to 0.3. So this is just customary in this kind of calculations of finite temperature and density. But notice that the thermal gluon mass involves the chemical potential, quark chemical potential, and the temperature in this fashion. All right, so what we need to do is to compute the imaginary part of this diagram. This, of course, is cutting this diagram here. And for that, we need to perform the sum over Matsubara frequencies, which involves a gluon function, either L or T, and a fermion function, which is taken, as I said, as a free quark. So what I want is the imaginary part, and for that, it's easier just to resort to this equation, which involves the spectral densities of the particles that I'm cutting. These spectral densities are these rows here. And then these are the distributions, the Fermi-Dirac distribution and the gluon distribution. And of course, this delta function that makes this overall work. For the spectral density of the quarks, or the fermions, I use the free spectral density. And for the spectral densities of the gluons, of course, these come from the Landau cuts. In other words, this is Landau damping. Otherwise, the process is not going to happen. So the Landau damping part of the spectral densities are these. I know it looks cumbersome, but it's straightforward. It's as I said, this is textbook formula. Then I put them together. This is again, this is just cranking the wheel. I compute the interaction rate, and it just happens that the interaction rate looks like this. And these functions here are the functions that multiply the spectral densities. Once we take the trace and we get rid of all of the gamma matrices and stuff, the interaction, the integration region is defined by this. These details are in the publication. If you want, I can go ahead, but I think this at this point is just as I said, ranking the wheel. There is no more to that. All right, so these are the explicit expressions for these functions. Let me actually point out to the fact that the first calculation we did was for massless quarks. And then we realized that if we put in the mass, it's actually easy. The phase space opens up, and so the interaction rate becomes even stronger, and therefore the relaxation time smaller. So that was important. Anyway, so we compute the total interaction rate. We integrate over all of the possible phase space. All of the distribution functions are already accounted for in this gamma, which depends on the energy. Therefore, the only remaining integral is over the overall phase space, which is the volume times this integration over momentum. The volume for two colliding spheres of radius r and at the impact parameter b, which is this ellipsoid that I talked about is this one, so we can put it in here and have the information of R and B, and therefore at the end the relaxation time is just the inverse of that interaction rate. All right, last, I promise this is the last ingredient before going to the phenomenology. We need an estimate of the angular velocity. And for that, what we did is to estimate the initial momentum using URQMD and the initial position of all of the participating nucleons for different impact parameters and different energies. And these are the points here for the different impact parameters that are shown here. So we try to represent these results with an analytic formula, and lo and behold, this formula nicely reproduce all of this behavior. These are the solid lines here as a function of energy. So it's nice. We have a handle on the angular velocity as a function of the collision energy and the impact parameter and the reaction volume. Sorry, the volume, the nucleon volume, the nucleus volume. That looks like this way, and it's a very nice way of representing these Monte Carlo results. All right, so what? Many ingredients. Let me just remind you that what we are pursuing is the intrinsic polarizations for S and anti-S quarks that come from the quark gluon plasma. What I argued is that we need to first compute the relaxation time. And so this is this tau. And I do it here for different conditions, different quark chemical potentials, different collision energies, and with and without mass. Without mass is this broken line blue and red here. And with mass is the solid lines here. So you see, with mass, the relaxation time becomes even smaller for the largest collision energies. It's almost always smaller than the case with massless quark. So you see, if the chemical potential is 0, this is the blue case, the relaxation time is large, but when the chemical potential is large, the relaxation time becomes even smaller. So this is nice because that will mean that the relaxation time is within the lifetime of the system, which is thought to be at most 10 Fermis or so. And it becomes even better when the temperature increases. And of course, when the chemical potential increases. So this also adds to the idea that for lower collision energies where we can achieve the largest chemical potential values, then we will have a larger polarization. Well, this is the case for the anti-quarks. You see that the anti-quarks compared to the quarks, you look at the scale here, the vertical scale, the anti-quarks case increase, the relaxation time increases, so it takes longer to anti-quarks to align their spins with the thermal vorticity, but still for large temperatures, this is still for massive quarks within the lifetime of the system. So this is also nice. Next, we define what is the intrinsic global polarization. We have the relaxation time. So let's imagine that we have a system in which we have an initial number of quarks which don't have their spins aligned. And so we want to know what is the number of quarks that don't have their spins aligned as a function of time. This is the time. And so in order to depopulate this number of particles which started not having their spins aligned to the thermal vorticity, then as a function of time, the number of particles that don't have the spin aligned is this formula. So those that have the spins aligned are the complementary. So this is 1 minus that exponential times the initial number. And so we can properly call this factor here, right here, the intrinsic global polarization factor. So how it looks like, here it is. For quarks is the blue, and the intrinsic polarization is larger as a function of time. And for anti-quarks is the red. It's smaller than for the quarks. as a function of time. When time goes to asymptotic values, both polarizations are going to 1, which is what we expected. This is just an example for one impact parameter and one collision energy. All right, so let's put everything together. Let's resort to what we know is from the thermal model, the freeze-out curves without excluded volume, with excluded volume. Let's work with this one right here, the red ones. We know that the net baryon density and the temperature are related with these curves here for different energies, and these are the numbers that are listed here. So you see for 2 GeV square root of SNN collision, then this will be the temperature and the net baryon density achieved in the collision. When the energy increases, you get this relation between T and the baryon density. The largest density is achieved for energies between 4 and 8. SNN square root is 4 and 8. These are the Nika energies, by the way. This is what makes this experiment so attractive. And the relation between T and mu B and square root of S are these. So we put this as the temperature and the chemical potential as a function of the square of the collision energy. And these are the results. This is the relaxation time for quarks, and this is the relaxation time for anti-quarks. For quarks, as a function of the collision energy, the relaxation time increases. For anti-quarks, it has a dip and then it starts increasing again. For the collision energies of interest, look, we have some window of relaxation times in which this tau, even though it's large, it will still contribute to the polarization of anti-quarks in the way I showed here. So we put them together and then we produce these plots. So we assume that the lifetime of the system is between 1.5 and 4.5 Fermis, and the relaxation times as a function of energy are computed here, and putting everything else together, these are the plots that we produce, and as I said, it looks reasonable. So I don't want to overemphasize this result. I know there are many ingredients, but all of them have, say, from our point of view, are reasonable, and in other words, they contain both reasonable assumptions and are driven by a calculation which is reasonable. The main idea behind this result is that there is a phenomenological interaction between vorticity and spin, here represented by this vertex, which is not coming from first principles, but it's a way of putting in phenomenologically how vorticity and spin interact. The rest is a straightforward calculation in thermal field theory, and then just using the available information from the thermal model and from the information for collisions as a function of energy, of PP collisions as a function of energy, to have a handle on this amplification factor. Put everything together and then you get this result. All right, so let me go to the conclusions, and perhaps if there are any questions, we can try to address them. As a summary, I have presented a two-component source to try to explain the excitation function of lambda and anti-lambda. The essential ingredient is the intrinsic polarization, which can be computed in thermal field theory from the assumption of a phenomenological interaction between thermal vorticity and spin. Now, of course, all of these ingredients can be put into a Monte Carlo analysis to test the capabilities of certain experiments. And since we here in Mexico are heavily involved in MPD at NICA, what we are actually trying to put all of this information in an MC analysis using the MPD root framework to try to see to test what are the capabilities of the detectors that have been already designed and are being built to detect this kind of polarization. So that will be very exciting to see what happens at these NICA energies for these polarization properties. So with this, I finish. I again thank you all for the patience and also for attending, and of course Neda and Masoud for the invitation, and I'm open for questions. Thank you very much.
So thank you very much for this very nice and very clear talk. And there are a couple of questions by Efrain, I think.
Yes, please.
So,
thanks, Alejandro, for the beautiful explanation of everything. That is, my question is about the critical density that you are considering between the core and the crust. That there was a point where you had the theta function, you remember?
Right, that one, right?
Then I will expect that in the core you have already the confinement, and
right.
I think that the lambdas there should be less important than the lambda that you can have in the core. But at some point, I think that you were telling the opposite, that the main contribution comes from the core.
No, you see, I think this plot is more or less self-explanatory in the sense that for the impact parameters of interest, remember that this is the polarization is an impact parameter driven phenomenon. So for large impact parameters, those of interest, you see that the population of lambdas coming from the QGP, this is the red line, drops below the population of particles that come from the corona, which is the blue line here. So it's the opposite as you're saying, Efrain. For the impact parameters of interest to the polarization, there are more lambdas coming from the corona than from the core. That's the point.
But I think that this is a different thing, no? Because what you have to look is for the energy.
The energy dependence.
The parameter is already talking about the polarization because of the angular momentum.
Right.
But if you look at the energy, that is, if there are all the graphs that you had, where you have the square root of SNN.
Right. You mean the excitation function for measured by a star? This one?
Yeah.
There,
I think that that is, if you have more energy,
right,
then the corona has to be the one that is making the biggest contribution.
Actually, it is true. It is an energy-dependent plot. I'm sorry, I just showed here the case for some small energy, which is 7.7 GeVs. A similar plot will appear at any energy, given this model, of course. And what you can see is that, if I remember correctly, for the largest energy produces a largest density in the core. So for small impact parameter,
it means that you are going to have less lambdas because you will have more deconfinement.
Right. Okay. See, the number of lambdas, of course, can also be computed from QGP processes, and this is the one that I'm trying to show here. Yes, there is a competition. I completely agree with you. It's more or less better discussed, I think, in the publications. I'm sorry, I didn't go into that many details. Okay. But what I'm trying to get at is that indeed it is an energy-dependent number. That's for sure. There's got to be parameters involved. For instance, this cross section and everything is accounted for in those factors, and it's also an impact parameter driven number. So the combination of all of them is accounted for within this model when we produce these plots here. In other words, we are not assuming a fixed number of particles coming from one or the other processes. We are putting all of its glory, all of its impact parameter and energy glory dependence to produce these curves here. So you see,
you have both contributions, no, the core and the...
Exactly, both contributions are there. We are not ignoring them. We are just putting them as implementing the energy dependence of each one of the factors that appear. In particular, for instance, this one, W, has an energy dependence, and all of them, as I tried to explain. Yes, so all of them are accounted for. The specific numbers for the cross sections and everything are, you can find them in the publication.
At some point you were telling that the contribution coming from the core was more important. Okay.
No. As I said, it's an impact parameter and energy dependent factor.
Okay. Then the other question is, have you tried to see if the interaction vertex that you have for this self-energy diagram can be obtained as a expansion of the green function for the fermions?
It's a very good question. Very good question. See, first we wanted to try to see whether some phenomenological approach would yield some results which were within what we thought could explain this phenomenon. And so we were encouraged by the results because the relaxation time turned out to be smaller than the lifetime of the system, at least for this interaction vertex that I'm showing here. Now, that said, this interaction is phenomenological. There is no first principle calculation. So one can try to come up with something better. And of course, that something better has to do with the propagator that is going on here. Yeah. So we are actually currently pursuing that approach. We are trying to see whether we can come up with a better propagator.
And to see what limit, that term will be the more important one.
Exactly. So in order to have an expansion and try to see whether that has some resemblance of this kind of interaction. It's a very good question. And yes, we are thinking currently about that.
Okay, thank you.
Thank you.
Okay. Are there any other questions?
Yeah, I did
Igor.
raise the hand.
Yeah, Igor. Yeah, please.
Hi, Igor.
Hi, Alejandro. Nice talk. I have a simple question, actually. The question is this.
Your questions turn out to be never simple, man.
Well, as it gets, we'll see. Well, you are basically describing this more or less standard full core convention that you have vertical effect. This via the spin-orbit coupling translates into the polarization of lambdas. Everything seems to be fine, except for one thing. It's kind of a complicated mechanism, if you think about it, very complicated. And at the same time, there seemed to be a much simpler mechanism related to the fact that lambdas have a magnetic moment. The magnetic moment of lambdas is about -0.61 or something. And basically that means that they respond directly to the magnetic field, and that will create a polarization without any complications due to spin-orbit coupling. Why is that not the dominant mechanism?
Again, see, if that was the case, then one would expect to have a larger polarization for energies where you find the largest magnetic field, which is the largest energies available, even Rick energies, LHC energies. But even for semi-central collision, such as the one that is shown here, that's not the case. In other words, the polarization seems to be consistent to zero, with zero. So that points to something which, although is related to the centrality of the collision may not be related to the magnetic field. So again, when you diminish the energy, you see the largest polarizations, but then you know that for smaller energies, the magnetic field is even smaller. So that's why we tried to come up with some other explanation that was not magnetic field related. I'm not saying that magnetic field doesn't have anything to say on these results. It's been tried in the past, and my recollection, I may be wrong, but my recollection seems is that that seems to be a bit on the fringe for the explanation, but it may have some contribution. I don't know how large, but it doesn't seem to be the main contribution. That is our point. But this is driven. I mean, this impression is driven from data.
Well, the thing is, all the details that you were explaining about the vorticity are essentially could be in modified forms applied to the magnetic field. With the energy, of course, is the increasing temperature, and of course, increasing the decreasing the relevance of the magnetic moment simply because you have higher temperature. So it's not immediately clear to me, at least, that the energy dependence you are showing is sufficient to exclude that possibility.
No. I'm not saying. I don't think that it can be said that thing with such certainty. Exclusion is not the word. What I'm getting at is that there is an alternative explanation. It seems to me that does not require the magnetic field. Of course, it will be nice to assess what is the relative contribution from one or the other. It is just a matter of, as you said, the cranking the wheel. It's rather straightforward. The motivation, again, was that the attempts with magnetic field in the past seem to me, I may be wrong, seem to me to be not the favorable explanation. But again, it's just a matter of doing it again.
Do you know who tried it?
Right. I have not here though. Let me see if I have it here. No, but in those publications, I can dig them up in these papers. We give the references to attempts with magnetic fields.
Okay, sounds good.
I'll dig them out and then I'll send it to you.
I appreciate that. Thanks.
Sure.
I think there is a comment by Masood.
Masood?
Yeah. I wanted to comment about the dependency of the magnetic field to the initial.
Oops, Masood.
Sorry, I muted myself.
Yep.
Okay. I wanted to comment on the energy, initial energy dependency of the magnetic field. And I think also that magnetic field in LHC is much larger in the initial time than in RIC. It does not mean that it is always larger. You know, although it's very 10 times larger, but it seems to decay 10 times faster. So these two things seems to cancel out, and the final thing is quite similar. I don't know in what stage of the QGP evolution or the firebar evolution you are doing the computations. I was thinking about the effective vertex. I think you can modify it in a way that it also couples a spin to the electromagnetic fields. You have sigma alpha beta times omega alpha beta. I think that you can add something like f of alpha beta to omega alpha beta, and this might I think, include both effects together.
Yeah, it's okay. Let me comment on your two comments. For the first one, it's not clear, but it seems reasonable to think that the product of the lifetime times the amplitude of the magnetic field is sort of constant. It's not a constant. I mean, there is no first principle to think of that, but it seems to be reasonable. But what you're saying. That means that for LHC energies, although the magnetic field can increase a lot, its lifetime is going to be small. Now, for RIC energies, the magnetic field, the amplitude is less, but the lifetime is a little larger. Now, when I say a little larger, I mean something which is not that large. Our calculations, and actually from other groups, you can also see that the lifetime is about 0.1 Fermis. It's a tenth of a Fermi. Now, you may argue that some hydro calculations start their evolution at, say, 0.3, 0.5 Fermis, and that they get reasonable agreements for hadronic observable stuff. It's actually interesting. But I don't think of anybody that will argue that starting the hydro evolution from 0.1 Fermi is a good idea. In other words, it's very difficult to think, or I mean, there may be reasons, but to think that there is thermal equilibrium at 0.1 Fermi. So in other words, if it is a magnetic field driven phenomenon, that the polarization that is, it should come from pre-equilibrium. And pre-equilibrium then is a completely different ballpark. It's not this ballpark. Mm-hmm. So you cannot resort to think of a gluon, which is a thermal gluon, and there is, of course, no baryon chemical potential dependence and so on and so forth. So that is unlike the calculation that I presented in this seminar perhaps a couple of months ago, where the photon production could be coming from pre-equilibrium. I think that it's difficult to think that the polarization of quarks and anti-quarks, which are, by the way, not very abundantly present in this pre-equilibrium stage, could come from these processes where magnetic fields are important. Now, it is true that for smaller energies, Nika energies, for instance, the lifetime of the system is larger, and our calculations show that it's about 2 Fermis. Now, 2 Fermis is all right. However, the strength of the field is way smaller. So again, it's a trade-off. It may be that this magnetic field has some bearings at that energy, but its effect is going to be smaller compared to the effects that could be present at larger energies, although at larger energies they last less. So I think that this is a trade-off, and that's what makes me think that perhaps magnetic fields are not the most important contribution to this effect. The second comment has to do with your suggestion to include electromagnetic vertices here. But see, this is what I was trying to get at. We know that in order to include electromagnetic effects, it'll be better to write this propagator right here as having magnetic and electric field effects introduced, say, in terms of a Schwinger propagator. So I would argue against putting a phenomenological vertex here that includes magnetic and electromagnetic fields here. I would rather pursue the idea to see what to do here once you put in a propagator, kind of a Schwinger propagator here. That'll be, I think, that'll be my choice. But in these respects, that's what I was trying to get at when I commented on Efrain's question. I think this can also be done to include the effects of vorticity. So what we're currently pursuing is to come up with a propagator that has vortical effects here and see what we come up with.
Thank you.
Okay. Any other question? Seems that there are no other questions. Okay. So, Alejandro, do you hear me?
Yes, very well.
Okay, okay. I thought that I have lost my internet connection. Okay.
No.
Okay. So let me thank you again for coming and for this very nice talk, and also for your comments. Very informative. And we are looking forward to seeing the calculation of this propagator and this self energy with the vertical effect. You say that you want to replace this propagator by the propagator including vertical effect. How do you want to do that?
Right. It's we still don't know how to do it, but I think we are on the way to do it. It's not straightforward, of course, but
no.
I think it can be done. That's the idea we are pursuing right now. So in other words, if you have such propagator, then you don't need to resort to these effective vertices here, but you still have the information both of temperature and chemical potential coming from here, and the vertical effect coming from here. It's too cumbersome to put also the gluons into the vertical motion, although they could, but that is a bit outside our current scope. I think for the time being, we will concentrate on this.
Yeah. It would be interesting. Okay. Thank you again, and thank everybody for coming and for joining us. And okay, maybe we can stop the recording.